here in the US is mostly composed of senior software engineers from tech companies in Silicon Valley and prestigious CS students from top universities. In addition, we have strong support from international and domestic competition winners in our coach team. From beginner-level Python to classic C++ courses and competition honors courses, XCamp's curriculum is designed for students of all different levels. By participating in team-based competitions and facilitating frequent group study sessions, XCamp also fosters an environment of collaboration to build each student's confidence in their ability to code. As of mid-2024, more than 300 XCamp students have reached the USACO Silver Division and above, including 60 in the Platinum Division, and 27 were selected in the US and Canada national camps, out of which 15 were fresh in the 2024 season and 2 were selected for the US national team. In renowned high school contests, Stanford's Procol and UC Berkeley's Calico, and other prestigious US programming competitions, such as the Harvard Programming Invitational, Teams Code, and Lexington Informatics Tournament, XCamp students perform well, and we encourage students from being participants to problem writers and organizers. Our students received 13 MIT offers and many more from Stanford and UC Berkeley, thrilling us all. Here at XCamp, we believe that children have unlimited potential and can change the world through coding.
All right. Yeah, so like the video said, at XCamp, we have a lot of students in the silver above division, over 60 now in platinum, and there were 27 USACO finalists and CCO finalists. And we have 2 EGOI medalists and 1 IOI gold medalist, Brian Xue, who got 3rd, I think, last year. For our class system, essentially we have on-site camps, which happen during summer and winter in the Bay Area, and they last somewhere between 5 and 10 days, depending on if it's winter or summer and what division. For our year-round weekend classes, we have 4 quarters per year, and each of them are 10-week quarters. We also had USACO mock test classes, which happened during the USACO season. It's around 4 hours of mock tests, followed by 1 hour of lecturing. And we have the Grandmaster classes for advanced students in USACO Gold, Platinum, Camp, and IOI. And we also have the APCS A series. For our February contest silver problems, we've got problem 1, the best lineup, which was a greedy problem. And greedy is covered extensively in the 400H class. For vocabulary quiz, it's a tree and greedy problem, which is extensively covered in 400H and 302H. And for transforming pairs, it's another greedy problem, which again is covered extensively in 400H. Okay, let's go ahead and take a look at our problems and how we can solve them. Okay, and I think I'll just go over them in order this time, because as far as problem difficulty goes, I think problem 1 and 3 are probably easier, and then problem 2 is a little bit harder. But all 3 were not too bad in the context of recent silver problems. Okay, so for problem A, we're given an array of size n being up to 2 times 10 to the 5. And what we can do is we can start by moving one of the cows to the front, or technically like as front as you want. And then afterwards, we have to basically go through from left to right. And then for every cow, we choose to pick them or not in the final list. And whatever list we generate, we want it to be lexicographically as large as possible. And lexicographically as large as possible is basically just like you compare the first number, and then if they match, you compare the second number, and so on and so forth. And then whenever some number differs, the array with the bigger number is considered lexicographically larger. And then finally, if like you have an array like 3, 3, 2, and another array like 3, 3, 2, 1, then the 3, 3, 2, 1 array is longer after the part they match, and therefore this one will be lexicographically larger. Okay, so with lexicographically largest or smallest problems, there's a very nice greedy property, which is we can just consider for our current element that we're adding, it needs to be the largest element, right? Because if it's not the largest element, then we can get something like graphically larger by not adding this outlet and adding some later outlet. So let's just go ahead and start by solving this problem without the operation where we move a cow to the towards the front. So this is really simple. We can just track what the largest remaining element is, and if you are the largest remaining element, you just add yourself to the queue, right? So for example, for 4, 3, 2, 1, 3. We can add 4 to the queue because it's the biggest, and then 3 can get added as well afterwards. Now we want to skip 2 and we want to skip 1, and then we can add 3 as well, the final 3. And that gives us our answer of like 4 through 3 if we were not allowed to move anything towards the front. Now, of course, for this specific case, we can actually go ahead and move our last 3 to the to here. And that gives us 4, 3, 3, 2, 1. And in this case, we can take every single element because every single element when we get to it, it's the largest one remaining. Okay, and this yields us a decent, I think, n to the third solution, I want to say, or maybe n to the third log n, depending on how you implement it. But basically, for every single like cow, you just loop through how far up you're going to move that cow. And of course, there's like n cows. And for each cow, there's roughly n positions you can move them. So there's like n squared initial arrays you can start with for after doing operation 1. And then for each of these arrays, we can just loop from left to right and then just check, are you the biggest cow? If so, add. Otherwise, don't add, right? And then that part can be done in O of n. So one way to do this is once you have your array, you can compute like a suffix max, basically. So the max element here is 3. The max element among here is also 3, also 3, also 3, and then now it's 4. And then now when you go left to right, you can easily just check, is this element equal to the suffix max? And if it is, that means it's the biggest element in the remaining part of the array. Otherwise, it's not the biggest, so you skip it. Yeah, and that gives us n cubed, which works up to which works as long as n is less than or equal to like 750 in this case. Okay, and then to go for the full solution, what we want to do is, well, it's like a little bit wasteful to start by generating all the possible arrays, right? Because essentially, let's just think about when do we actually want to move a cow towards the front? So the only time it makes sense to move a cow towards the front is when we're about to skip a cow, but we can actually save that cow if we move someone to the front, right? So let's go through this example one more time. So here, again, we just go through from left to right, and we can take the 4 because it's the largest. We can take the 3 because it's the largest. And then if we don't have the operation, we have to skip the 2 because it's not the largest. But we realize that if we were to move the 3 up, we can now take 3 and then take 2 and then take 1. But all we really care about for now is that if we move 3 up, we can take 3 and then follow that up with a 2. And the question is, when can you actually save the current cow from being skipped with this move? And for that, it turns out they have to be the second biggest cow within the remaining range. Because, yeah, so let's say it was like 2, 1, 3. Then in this example, we can move the 3 up, take the 3, and then take the 2. But let's say there was like another big element, like another 3 out here. Then this 2 cannot be saved no matter what, right? Because even if I move this 3 up and I take that 3, I still can't take this 2 because there's a bigger 3. Because there's a bigger element to the right afterwards. So that's essentially going to be our check. So we want to maintain some sort of data structure where we can start by throwing everybody into this data structure. And I guess let me just make a requirement list for data structure. Okay, the data structure, like requirements. So the first thing we want to do is we want to go to like add an integer, because initially we're just going to add everyone in. And then we also want to be able to remove an integer, because whenever we process a cal, this cal is no longer like part of our consideration. And then the other operation we need to do is we need to be able to query like the largest elements. So who's actually the largest? And we also want to know who's the second largest. Right. And then our algorithm will just be, we go from left to right. And then if the current element's the largest, then we just go ahead and add them into our final answer. If the current like element is the second largest element, then what we can do is we can move up the largest element, take that largest element, and now we're going to take the second largest element. But we can only do that once, right? Okay. And so a fitting data structure for this, the easiest one is probably just using a multi-set. Right, it pretty directly supports all the operations we want here. We can add integers, we can remove integers, and we even allow duplicates, which is good. We can find the largest element with like r_begin, for example. We can also get the second largest element. I guess for this, we would do like set, like the multi-set dot end, and then minus minus it twice. And that gives you the second largest element. Yeah, so it nicely supports all those operations. You can also use a priority queue. This works as well. So again, adding an integer is easy. Removing integer is slightly trickier because now you have to like lazily remove, because you can't like arbitrarily find an element to remove it. Yeah, so you can keep like a Boolean array for like which elements have been removed. And then when you query for the largest element, you have to first remove all the invalid ones, and then you can, yeah, and then it works. And then for second largest element, similar, but you should have to pop off the largest element, then look at who the second largest is, and then put the largest element back in. So it's like a little bit trickier with a priority queue, but it also works and it's probably faster. Yeah, multi-set works just fine for this problem. Okay, are there any questions on this one? Oh, and then our final runtime here is just like a log n, because we just scan from left to right, and then for every like each operation basically happens n times, right? So like we add everyone in initially, we remove everyone at most once, we query largest and second largest element at most n times total. Yeah, so overall just unlock it. Any questions? Okay. So I guess next let's actually talk about problem 3, because it's like the second easiest one, in my opinion. And the problem statement is pretty simple. So you're given 4 numbers A, B, C, D. So in this case, like, so for this first sample, it's like 5, 3, 5, 2. Actually, let's take a sample where it actually works. So 5, 3, 8, and 19. And what you want to do is you want to make it so that A is equal to C and B is equal to D. And there's only 2 operations you can do. The first operation you can do is you can add B onto A. The second type of operation you can do is you can add A onto B. So I think for this example, you should first add B to A. So you get 8 and 3. And then you add A to B to get 8 and 11. And then you add A onto B again to get 8 and 19. And this took like, okay, so I'll just do plus B plus A and plus A. And of course, this is 3 operations. And that's the best you can do. That gives you your answer 3. All right. So it's pretty tricky if we try to do this going forwards, because at every single step, I can either add A, like I can either add 2A, or I can add 2B. Yeah, and then so there's like a branching factor of 2, and then you can stop whenever like an element exceeds, like whenever A exceeds C, for example, you can stop, or whenever B exceeds D, for example, you can also stop. But even with that, it's not quite good enough, because the numbers go up quite large, right? Like up to 10 to the 18. So some sort of like BFS approach, where your state is basically like what's the minimum operations to get to some A and B. And then you can have your initial A and B just be equal to cost to 0. And then each time you either modify A or you modify B, this works up to only test cases 3 and 4. Yeah. Okay. Yeah, so this works up to like test case 4, where you just do like a 90 PFS, starting from AB, and you figure out the minimum distance to get to C and D. Okay. Yeah, and then for our main like major observation is that this problem is way easier if we go backwards. So if we think about turning C and D into A and B, it's kind of the same thing, except at every step it's obvious what you have to do. So if we're trying to turn C and D into A, B, let's just look at step 1. Well, and instead of adding, we'll just subtract because that's like the opposite of like adding A to B or B to A, right? So if we start with 8 and 19, like have to just subtract 19 by 8 to get 8 and 11. Because if you were to subtract like 8 by 19, you go negative, and then there's no way it can ever be A and B. Yeah, so operation 1, we have to do this. And then again, we have to just go ahead and subtract 11 by 8 again to get 8 and 3. And then our third and final move is also forced, where it becomes 5 and 3. And we find out, okay, we win in like 5 moves or 3 moves. And this works for like the impossible cases as well. So let's go through like, yeah, let's just go through the as first example. So we have 5, 3, 5, 2. Okay, this is not a great example because yeah, it just doesn't work right away. So let's do 5, 3 and 19, 8. So again, we have to start by just subtracting C. So we get 11, 8. And then we have to do it again, and we get 3, 8. And at this point, we can stop because like C is smaller than A, so then it's clearly impossible, right? So if we do some algorithm where you go in reverse and you just keep subtracting until either C or D is less than A or B, or if they're both equal, then you're done. Then this gives us a O of, well, in most cases it's pretty fast, right? Like if C and D start roughly equal to each other, we're like, yeah, so in most cases, it's decently fast, but like worst case, it's still O of like C plus D runtime roughly. And one example here is like if C starts at 1 and D starts at, I assume this is 10 to the 18, then your number of like moves needed is going to be like 10 to the 18 minus 1, right? To get it down to 1 and 1. Okay, so this is pretty solid, and it gives us the next few test cases, 5 through 7. So check. And now we just need to figure out how to optimize this to be fast enough for even up to 10 to 18. Well, so if we look at the example here, where it's really, really slow, and I'll use a slightly smaller example. So let's say you have A, B, C, D. This is like 1, 1. This is let's do a slightly different example. Let's say this is 2 and 99. Okay, so first of all, this works, and we can tell like visually that works because you can just keep on subtracting. And you know you're eventually going to get down to 1 because this started as like an odd number, and therefore it's going to stay an odd number whenever you subtract by 2. So eventually we'll get down to like 2 and 1, and then now we'll subtract 2 by 1, and then it's 1 and 1, right? So we know this is eventually going to work. Now the question is, how do we like quickly calculate the number of steps it takes without simulating each step separately? Well, the main thing to notice is that a lot of the steps are pretty repetitive, right? Like you're just doing -2, -2, -2, -2, -2. So basically you can just compute with a little bit like math, what their difference is. So in this case, their difference is 97. And we know we're going to subtract by 2 every single time until like C is greater than D. So you can just go ahead and take 97 and figure out how many times you need to subtract by. So you're going to just divide this by 2, but you want to ceiling this, and that's the number of subtractions you're going to do. And the formula for this in general is if you have A over B ceiling, with integer division, it's equal to A plus B minus 1 over B. And the idea here is you just add B minus 1 to A, so that if A is already perfectly divisible by B, it doesn't add anything to your answer. But if A is not already perfectly divisible, it's going to increase your answer by 1. And that's exactly what the ceiling function is. Okay, so we just go ahead and compute the ceiling of the difference divided by the smaller number. And then that's how many steps we can like fast forward by in a row. And we just figure out what's the result at the end of that. So we can jump from 299 directly to 21, and then we can jump from like 21 directly down to 11. And now the number of steps is going to be logarithmic. So we've achieved O of log C plus D. Okay. Yeah, and this works even if you have a ton of test cases. So our final run counts like O of T plus log C D. Are there any questions for this problem? All right, then let's talk about our third and final problem 2, vocabulary quiz. Yeah, so this problem statement is already like a little bit interesting / weird. They don't actually like give you any words, right? And so they give you this like weird format that ends up being a tree, and specifically it's like a trie, where basically in a trie, every node denotes a word, and then every edge denotes what letter you add to the previous word to form the current word. So let me give like an example of how a trie works. Not that you really like have to know it for this problem actually, but okay. So let's say you had a word like ABC, and you have another word like ABB. So you would construct the trie like this. So you would have like some root node that is just the empty string basically. And then this branches off to the left with an A. So this string is just A. And then this branches, let's say, towards here with a B. And so this string is the AB string. And then you can branch left again with another B. And this node is ABB. And you can branch here as well for ABC. Right. So every node is just like what the current word is. And then whenever you cross an edge, you just add that like character onto the end of the previous word to form your new word. And this is a really efficient way, a pretty efficient way to like store a list of strings. Yeah, which is how this input works effectively. Now, except they don't actually tell you what the letters are. They just say it's some letter that's like different, right? Okay. And for this property of like you're going to be given the words that are not a prefix of each other in a permutation. Basically, that's saying you're going to get all these leaf nodes in some arbitrary order. Because any node that's not a leaf node is a prefix of something else, right? So like A is of course a prefix of everything here. AB is a prefix of everything here. This leaf node, ABB, is not a prefix of anything. And same thing with this one. ABC is not a prefix of anything. Okay, so that's just to kind of like digest the problem. Yeah, so essentially and then I guess let's talk about like, how do we figure out just conceptually how many like letters need to be read off before you can figure out that word, right? So in this example here, you would have to read 3 letters before you know that it's the word ABB or it's the word ABC. Because the first letter read is always A, the second letter read is always B, and then you need to wait for this third one to know. But if we draw a different looking like tree, so let's say our tree looks like this. Okay. Yeah. So let's say our words are this one, and this one. I guess I'll just label them 1, 2, and 3. So suppose the first word that gets read off is word 2. Then the number of like letters that we need to hear is going to be 3, or sorry, 2. Because first, she's going to read this letter, whatever it is, and then we don't know which word it is still. And then afterwards, this letter gets read out, and now we can uniquely identify this word, right? So that's why it would take 2. But let's say the word 1 was being read out first. Then after just one single letter, this letter, we already know that like there's only one possibility left, right? So the general idea is, so yeah, conceptually, we just think about it as you start from the root node, and then you just read your letters out one by one, which equates to traveling down the subtree towards the leaf node. So in this case, I'm going to travel towards here. And then whenever within this whole entire subtree, there's only one leaf node left, that is when you can stop, right? Because you don't need to follow it the rest of the way down. You know it's uniquely this one. Whereas like for the right side here, and I can, I guess, draw this a little bit differently. So for the right side here, after we hear letter 1, we still don't know which one it is among these two. After we hear letter 2, again, we still don't know which one is among these two. But after we hear letter 3, now we know, like within this subtree, there's only this possibility left. And that's when you can stop for the current one, right? So conceptually, we can just run this algorithm. And then whenever we find a word, we just delete that like node. So let's just say in this case, we delete all this from the tree. And then we run the algorithm again. And then let's say it's the left node this time. So then after one single word, we find it here. And then we can just delete this whole part of the tree. And then finally, whenever, like, finally, you don't need to hear any letters because now the whole entire tree, like starting from the root, only has one leaf node. So then you just finish with a 0 and you can delete this whole tree, right? Okay. And so if you just naively simulate this, it's, I guess, a bit tricky to implement, but it probably works with at least test cases 4, 5. Um, I don't think it works with the second like subset of test cases, just like naively simulating. Yeah, so let's talk about a better method rather than like simulating the deletions and everything. Okay, so instead what we can do is we can just think about it as, instead of like literally deleting all the nodes, we can kind of like simulate deleting by just tracking for every single subtree how many active leaf nodes there are. So I'll go ahead and label them as like 3 initially. So initially this has 3. And then this side has 1, 1, 1. This is 2, this is 2, this is 1. Okay. And then now what we can do instead is we can start from some like leaf node. Let's say 2 gets called first, right? Then instead of starting from the top and going down towards it, we can actually just start from node 2 and then go up, as long as whenever we're going, like, we keep going up until we find that this subtree is not 1. Like the number of active leaf nodes within the subtree is more than 1. That's when we stop. So the idea here is like, okay, we start with like the depth of this is 1, 2, 3, 4. So like initially we say, okay, our answer is currently 4. And then we notice, oh, we can go up to our parent because that's also a 1. So, okay, our answer should actually be 3 because we could have stopped here. And then from here, we realize, oh, we can't go to our parent because our parent is a 2, right? So it's like from the top to the bottom, like stopping at this 2 is not good enough. You have to stop at a 1, right? So basically you want to figure out the highest like node, that's a 1. All right. And so if we do this algorithm, then overall it's pretty fast. And I think it might work for test cases 6 through 10. And then the main idea afterwards is, after you have this node done, you just loop through all its parents and you subtract their values by 1. So like this now turns into 0, this is now 0, this is now 1, this is now 1, this is now 2. And the reason, and after we do this, then like, let's say we get node, this node next, then we can walk all the way up to here. And that's how we figure out its answer should just be 1, right? Okay, yeah, and this works for test cases up to 6 through 10 because the sum of the length of all words in the word bank does not exceed 10 to the 7th. So we know for every word when we remove it, like we loop through all its parents, but like the sum of all the looping we have to do does not exceed 10 to the 7th. So this works. But now for the final version, I'll go ahead and present 2 ideas. One that more directly just one that's a more like direct optimization to our current algorithm, and I'll present an alternative algorithm that's potentially easier to come up with, but uses some like harder concepts. Okay. So the idea here is instead of looping through all your parents and updating them one by one, we're going to do this thing called like lazily updating, which means we're not going to update all their values until they need to be updated. Now, what does that mean? So let me give an example here. Suppose my tree looks like this. Yeah, this should be enough. Okay, so my tree looks like this. Initially, this node has 3 active, 3 active, 3 active, 3, 3, 1, 1, 1, 1, 1, 1. Right? All right, so suppose I start from this node. I'm like, okay, I can go up to my parent because my parent also only has 1 active node. And then I can, I can't go up any further because this node has 3, right? And then now we do the deletion process. So I want to remove this node, which means I set this to 0, I set this to 0, and then I'm going to set this to 2. And then naively, I walk all the way up the tree and set all of these values to 2, right? But like, if we think about it, do we really need to do this last part where we set all their parents to 2? Not really, because it doesn't matter if it's a 3 or a 2. We can't walk to them yet anyways, right? And so we can actually stop our updating process right here. So I'm just going to update this to a 2. But I'm also going to remember this lazy value of -1. And all this means is, like, I've been really lazy at this point, and I have to do this -1 to every node above me up to the root, but I haven't done that yet. So I'm just going to go ahead and remember this -1. So that in the future, when it's important, I will actually do that. Now, let's go ahead and do the same thing for this node. So once again, if we start from this node, we can go up to its parent because its parent value is just 1. And then we can go, and then we have to stop there. And again, let's do our updates. So this gets changed to 0. This gets changed to 0. And then this would get changed to 1. So at this point, you can, it actually, okay, so for now, we'll just leave it as 1. And yeah, we're going to go ahead and set the lazy value now to 2. Because now at this point, like, we have a -2 that we need to do to every single node above us that we haven't done yet because we're lazy, right? But now finally, when we go through this node, again, we'll do the same process. We start from here. We use a different color. And then we realize we can go up because our parent is a 1. And then we can go up again because our parent is still a 1. And now from this node, we want to know, can we go up again? Now, if we just look directly, we see a 3. But remember, this is not supposed to be a 3. This is supposed to be a 1 because this -2 should have been applied to every node above us. So before we look at our parent value, we check, do we have a lazy value? Again, this lazy value means I need to subtract my parents by this amount, right? So if my lazy value is not 0, I'm going to go ahead and do that before I look at my parent. And so that's going to change the parent value to 1. And then we can clear out this lazy value because now I've done my subtraction. But now this parent node has not done the subtraction to its parent nodes. So we're going to go ahead and move the lazy value up to my parent, right? So generally, like at a given node, before you look at your parent, you check, do I have a lazy value? Let me just go through that one more time. So at this current node, we have a lazy value of 2. So before I look at the parent node, I'm going to move the lazy value to them. So this means, okay, I have a lazy value of 2, which means all my parents needs to be subtracted by 2. So I'm going to do that now before I look at them. So we first change this 3 to 1 because that's how much our lazy value told us to change them by. And now we can go ahead and set this lazy value back to 0 because now we've actually done the work. And now this parent node now needs the lazy value of -2 because it has not subtracted the values above it with the 2 yet, right? Yeah, and that's the general procedure. Okay, and now after we move this lazy value, we can now look at our parent value, and it's the actual true value, right? So again, our parent is a 1, so we can go up the node again. And now from here, we do the exact same thing. We say, oh, we have a lazy value of 2, so let's go ahead and move that to our parent node. So our parent is now a 1, and this lazy value 2 gets moved here. And we'll keep going. So this allows us to go all the way up the tree and realize, oh, we could have stopped at the root node, and therefore the answer for this final, like third node, or the third query, should be 0. Right? And what's the overall runtime of this algorithm if we have this like lazy value and stuff? Well, let's go ahead and analyze all the parts. So step 1, we need to build our tree, which we can just do with the input, not too tricky. Yeah, and then we need to pre-compute the number of like leaves at every node or at every subtree, which you can just do with like a DFS, right? So start here, DFS all the way down and back up. So basically, yeah, you're just running a DFS to compute the number of leaf nodes at every singular subtree. And then finally, we have our lazy value part, which can be a little bit tricky to think about in terms of runtime. But essentially, well, first of all, the runtime is just O of n. And now let's get to why. Effectively, if you count the number of times each node gets looked at by any of its children, the total number is going to be O of n plus m, where n is your number of leaf nodes, right? So the idea is starting from every singular leaf node, we look at our parent, and then if this node has 1, we can look at its parent again, right? Now, the number of times that the node's going to be 1 is at most n times overall, because basically, if you think about for any given node, let's say it starts at 4, and then gets subtracted down to 3, and then gets subtracted down to 2, and then gets subtracted down to 1. Well, it can only be 1 once, and then it becomes 0. So yeah, the number of times where a node is 1, and therefore we need to keep looking up, is going to be at most n times. And then we also start like n different like walks up the tree. So our overall number of operations is just O of n plus m, which is just O of n, because m is at most n. Yeah, and that gives us our really neat O of n runtime, and that fully solves the problem. Any questions with like the solution before I move on to the second one? And I assume this is the intended silver solution, because basically you're just doing DFS and then you start from like nodes and you walk up, and then you have to be a little bit creative about how you do the updates so that you don't time out. But like nothing here is like too crazy hard algorithmically, right? Like we're not using fancy data structure for like algorithms. Okay, so let's go for a second solution that requires like harder algorithms / like topics, but might be more intuitive or easy to come up with if you are already familiar with those. Okay, so we're going to use the same idea of like you start from a given node, and then you basically want to walk up the tree until you find that until you find some subtree where there's more than one active leaf node in that subtree, right? So essentially, in this case, if we start from this node, we know the furthest up we can walk is only here, because if we walked up to this node, there's 2 leaf nodes that are active within the subtree, and therefore this is not a valid node we can go up, right? Now, essentially, there's this concept called lowest common ancestor, abbreviated to LCA, which is basically if you're given 2 nodes, you can use LCA to compute quickly or I guess the LCA concept is just which node is the lowest node. Again, lowest being like the deepest down one. So this being depth 0, these nodes are depth 1, depth 2, depth 3, depth 4. So the lowest node here is at depth 2, and specifically it's this node. So you can use, so the concept of LCA is just that. And then you can compute this in O of n log n. So you can do some O of n log n pre-compute, and then plus q log n to query. So for every single query, after we've done the pre-computation, you can do this in log n. There are also some ways where you can do this in like O of n log n pre-compute and O of like O of 1 query, but it doesn't really matter. The overall point is just that the runtime is n log n overall. Yeah, and this is really helpful for this problem specifically, because if you think about like for any given node, how far you could walk up the tree is bounded based on the first leaf node to its left and to its right. I'll draw a slightly bigger tree to illustrate this idea. So suppose you have like another part branching off here. Right. So if we think about this node, so if we're creating this node, how far up we can walk, we don't really care like where this node is going to be involved, right? Or where this node is going to be involved. Involved meaning there's some subtree that contains both this one and this one, right? It doesn't really matter because we know that we're bottlenecked by either this one or this one. So conceptually, you can basically run DFS order, and then you get the ordering of leaf nodes from left to right. So this would be node 1, this would be node 2, this would be 3, this would be 4, this would be 5. And then you have this ordering. So then starting from a given node, you can go ahead and figure out who's the node to the left of me, who's the node to the right of me. One possible data structure for this is just like a set, right? So you can store like a pair in your set. So you can first store the like DFS number, and then you can store the actual node number. And if you sort like this, it'll sort based on this, right? Yeah. And then you can just find this element and then do previous and do next. And once you get these two, once you get these two leaf nodes that are to the left and right of you, you can now just query for their LCA. So that gives you this node and their LCA here. That gives you this node. And you know that's how far up the tree you can walk. That -1 to be exact. Okay. So it's like so for like this node, you're bottlenecked by this one, and you have to make it past this node. So then your answer would just be, you can only go up to here. And then you can also just like pre-compute the depths, and that gives you your answer as well. Okay, so that's the rough idea for solution 2. And I won't really go into like LCA because it's not a silver concept. This is more of like a gold or platinum algorithm. But yeah, it can be used here if you are already familiar with it. But if not, that's okay. There's like other ways you can solve it with just silver topics, like the first solution I presented. And then this runtime would just be overall and log n, which should be fast enough for 10 to the 6, as long as you don't have really bad constant factors. Where is it? Oh, here, 10 to the 6. Okay. Okay. Any questions about any of the problems? Cool. Yeah, that's it for this silver contest.